with Andreas as we go along. So I'm very happy to introduce our first speaker, who's Thomas Ball. So Thomas is a partner researcher at Microsoft Research, very well known for his many works, in particular on the SLAM project, which was, of course, a hallmark in the sort of advancements of formal methods, in particular in industry. And so he'll share with us today some of the experiences of him working on that project, and in particular the involvement of Andreas in this project. Yeah.
Dankeschön. Guten Morgen, Damen und Herren. Ich heiße Thomas Paul, and now we get to English. Okay, so Andreas, welcome. It's time to get this party started. As you see, I came for a party. Abstract interpretation, software model checking, and beyond. It's been 25 years since the SLAM project started in 1999 with Sriram Rajamani and myself, and you joined us very early in those times to spread the good word from Patrick Cousseau about abstract interpretation. In fact, a lot of what I'm going to say really owes to you, channeling abstract interpretation. The other thing I want to say is we're both dog lovers, and I was so excited to see this picture on the workshop page. What's the name of your dog? Zartine. Zartine? Tartine. Which means kind of sandwich. Oh, Tartine. Okay, Tartine meets Loki. So Loki as in, Loki. Not the Marvel Universe Loki, but like, Wagner Loki, Nibelung and all that. Okay, so we're gonna talk about Andreas. So of course we have to start by going to Google Scholar and seeing sort of. I really want to know about the meaning of life, but that's a talk for another day. 1993. That's when I got my PhD. You were already producing lots of papers. But if you notice something about the years here, it was the early 2000s. So it was the start of software model checking, which was building on hardware model checking, program analysis, theorem proving, all these things coming together. And we'll talk a little bit about that time. So the overview of my talk, we're going to talk about safety, the early 2000s and the rise of software model checking, abstract interpretation meets the SLAM project. We had our first paper with Andreas, which was way back in 2001. And then we're going to, of course, we can't go on without talking about liveness and termination of processes as well as programs. And it really was a remarkable time where Andreas and Andrei Rybelchenko really started to tackle theoretically the foundations of termination of programs. And then of course we'll have a postlude. Okay, so in the spirit of the day, which is AI, we can't avoid it now, we move on to safety. So what could be more safe than a Samoyed driving a Tesla on autopilot? We move on to safety. And if you don't know, we did this little thing called the SLAM model checker. And what was that? That was, as Wes Weimer talks about very briefly in English here, not formally, SLAM is a software model checker. It abstracts C programs to Boolean programs and model checks the Boolean programs. No errors in Boolean programs implies no errors in the original. An error in the Boolean program may be a real bug, or we may refine the abstraction. So at a high level, that's what's now known as counterexample guided abstraction refinement, or CGAR. And that's what Sriram and I and others were exploring in the beginning of the 2000s. And so that was a really interesting time. Now we did more than just create the project and write papers. There was something called static driver verifier. So this was the idea that at the top here, you had all sorts of rules about how to write a device driver, and a device driver plugs into Windows and gives you access to peripheral hardware, whether that's a printer or a network card or things like that. And we would codify those rules that were in English in precise safety automaton, which was called SLIC, and an environment model to model the operating system kernel. And this SLAM process that Wes just described in English would produce defects like error traces, or it would say, hey, I couldn't find any other errors. And of course, there's a third unspecified arrow there, which would be the thing looping forever. But we'd just turn it off after a few hours if it didn't say anything. Of course, what did it analyze? It analyzed the driver source code in C. And so this actually, since 2004, this tool has been available and actually mandated by the use of device driver writers. And there was a core team, including myself, Ella Bonamova, Byron Cook, who will be coming later, I understand, Vladimir Levin, Jakob Lichtenberg, Kamak Harvey, Bohus Androsek, Sriram, and Abdullah. And we were the core team that implemented static driver verifier on top of SLAM and delivered that. And for many years, I think device drivers have been sort of this benchmark against which many software model checkers are measured. Okay, so back to abstract interpretation. So in 2000, Sriram was coming from model checking, I was coming from program analysis, and Andreas came in 2000 with the declaration of abstract interpretation from Cousseau. You had spent, what, a year with him or so? Maybe? Oh, just a month? Oh, okay, you're a very fast learner. So what I learned from, this is a slide that if you were at the Cousseau 30 years of abstract interpretation you saw, it was my synthesis of what I learned about abstract interpretation from Andreas. So the declaration of abstract interpretation was a statement of principles about program analysis that you should compare interpretations, different interpretations of abstract interpretations of a program, you can compare different interpretations to one another, you can compose them algebraically, and by all means you should celebrate infinity. Like if you do a finite abstraction, you know, just go away. So these, and I also love alliteration, so CCC. So we had CC77 and in the spirit, 3 Cs. That's how I always remember abstract interpretation. We're always doing comparisons, we're composing new abstractions out of old ones, and we're, by all means, we have infinite lattices. So at that time, you know, I also said, well, where did the 3 Cs come from? So Galois, of course, was all about Galois connections, so that's the comparison. Galois there, and Turing, of course, the infinite tape and infinite programs. We have to celebrate infinity because, of course, these programs may never terminate. And then in terms of composing, then thinking of algebraic approaches, thinking of Scott, who was a PhD student, I believe, at Tarski. So this was, you know, this was synthesized into Cousseau's mind. And of course, what happened was Andreas took that in 1 month. You knew a little bit about it before, right? Yeah, and he came to Redmond, and he showed us the way. Now, at that time, of course, I was steeped in data flow analysis. So data flow analysis, sort of from Kildall, you know, is sort of represented by maybe the United States, and then abstract interpretation by France here. But they share sort of something in the intersection, which is, of course, a control flow graph of a program, semantics via semi-lattice and monotone functions and a least fixed point, but over on the top there, we're generally concerned with finite height domains, efficient algorithms, compiler optimization, right? Down here, compare, compose, celebrate infinity verification. So Andreas was coming from, I think, the lower right here, having visited Patrick and Radia, and we were very much up in the upper left here. So for those of you who don't know abstract interpretation, who has never heard of abstract interpretation or doesn't know what it is? Okay, we're going to fly through this. We have the integer sets in the upper left. That could be reality. That could be our concrete domain. We can abstract it various ways. We can do intervals, so we have a rectangular abstraction. We can go to an octagonal abstraction, which is more precise than intervals. And then we can go to like polyhedral, where we get a more precise abstraction, but there are many points still inside the abstraction that weren't in the original set. So that's the first idea of comparing. So what happened with Andreas was about composition. He came to Sriram and myself in 2000, and he said, well, you have this great algorithm that takes C programs to Boolean programs. Okay, what abstraction does it actually compute? And Sriram and I were like Homer Simpson. We were like, duh. I mean, we were just like, well, we don't know. We proved it correct. Like it's an over approximation of the semantics of the C program. And you know, we proved it. It's sound. He's like, that's not good enough. You have to tell me precisely what the abstraction is. And so we were a bit at a loss. We didn't really know. So Andreas said, well, what you should do is apply the ideal. So we were doing predicate abstraction. So if we look up at the top, say we have 3 predicates, x greater than 5, x less than 5, and y equal to 5, and we're thinking about the effect of the assignment statement x gets y. By the way, I haven't talked about this slide for like 15 years, but it just comes back like yesterday, like I was riding a bicycle. So we can take the interpretation. We can take the abstract bit vector 0, 0, 0, and we can ask about its concretization into the actual state. Actually, I'm going the wrong way, right? That's concretization. So what does 0, 0 represent? It represents all the states S such that x is equal to 5 and y is not equal to 5, right? Because the predicates x greater than 5 and x less than 5 are false. So x must be equal to 5. Right? And the predicate y equal to 5 is also false. So 0 here represents the predicate being false, 1 representing true. Okay, and then what we do is we do a strongest post condition, and we would get this representation as a set of states that now x is equal to y and y is not equal to 5. And then if we abstract it back into the predicates, the 3 predicates that we would have, we would get 2 bit vectors. We would say, well, what you know if you're only in the world of the 3 predicates P is that either x is greater than 5 and y is not equal to 5, or x is less than 5. So is that clear? So that's the precise Boolean abstraction that you would get by taking a particular set of bit vectors, getting the formula, the concrete a realization of that, pushing it through the transformer. That's the best you can do with Boolean abstraction. Okay, but here's what we get when we apply SLAM. So we won't talk about the abstraction we compute, but we take 0, 0, 0, and SLAM, we get this. We get 4 bit vectors, which includes the 2 we got from the ideal. So something's going on here. We're not the most precise. So what are we then? And Andreas puzzled it out and figured it out. He said, well, what you've got is a case of Cartesian abstraction, forgetting. So Cartesian abstraction is you take a set of tuples and you approximate it by a tuple of sets, because there are too many tuples in your set, so why not just have a tuple of sets? And so if you take this precise description we got and you do the Cartesian abstraction, what you get is whenever there's disagreement in a position, you just essentially go to star. So really and then if we think of what the concretization of star star 0 is, it's the set that we had, that SLAM had. So basically what he's saying is like, yeah, you're basically losing information. You're losing information. You're losing the correlation between these 2 predicates that talk about y. Okay. And so SLAM abstraction was not, as perhaps Sriram and I thought, although I didn't even know we had the language to think about it, was not like the precise Boolean abstraction, which you would get by taking some bit vectors, abstract domain, concretizing, doing strongest post condition, then abstracting. Rather, it was this composition, right, where we did the Cartesian abstraction, then we did the Boolean abstraction. So we would lose actually at the end there. We'd lose on both sides. Okay, so that's what Andreas taught us, was that we really had to think about decomposing our abstraction into smaller abstractions, and only then could we understand what was going on there. Okay, so that's really thank you, Andreas, for so much. Andreas has always been about fundamentals and really understanding, digging in and understanding what is the key principles underlying a process. And here, again, it was really his visit, and there are many other stories how Andreas explained SLAM to Cousseau, but I'll let you explain that. That's a whole other story, right? And somehow you didn't quite convert him totally, but he came to understand it. He actually wrote a paper or something about finite abstraction, right, in the end. Yeah. Okay, so now we move on to termination. Okay. We can all go to sleep now. All right. So this is the slide that I had in Patrick's talk. At the time, Ratatouille was out, and the thing about ratatouille was the chef has infinite possibilities. Like you think, oh, there's only finite ingredients, but you can make an infinite number of recipes. And in the same way, why restrict yourself to finite lattices? I mean, that's ridiculous. You know, an infinite lattice, a chef with an infinite lattice, it's a recipe for tasty abstractions. And of course, you know, Cousseau was all about this. Why restrict yourself to finite? And of course, this shows up in many domains. So when we think of really what is going on in SLAM, it's a process, it's not an algorithm, because it doesn't have a termination guarantee. So we take a program on the left-hand side, we take some predicates, we abstract it to this Boolean domain over here, we do some model checking of it, and if it passes, we're fine, but if we get an error trace, we have to do something to say, is that error trace feasible or not? And we can just go around this loop for a while. So the next question Andreas asked is, well, and many people asked, well, do you have any guarantee? Is it going to ever terminate? Because you can keep refining and inventing new predicates, and depending on the power of your logic, you may not be pleased. So here, Andreas came to the rescue again and helped us in terms of thinking about relative completeness, which is obviously a very well-known concept of this abstraction refinement for software model checking. So this is the abstract, you know, automated methods for undecidable class of verification problems cannot be complete. So Andreas said, well, let's think about an oracle that does widening. So, you know, during abstract interpretation, you know, if things aren't terminating, you can like jump and you can do this widening. And so there are many possible widenings. If you think of what SLAM was doing, or any model checker is sort of exploring a search space, well, why not incorporate widening into the search? You can choose different widenings at different times. And so the idea here was to compare software model checking to this fixed point iteration with oracle guided widening. And the result here was, I don't remember all the details, but it was basically, you know, if there exists a iteration with oracle guided widening that succeeds in proving a property, then you can do a particular form of abstraction refinement where you can also prove that. So it's again, it's a conditional, it's a relative termination property. If there's this oracle that will terminate and prove the property, then a particular form of abstraction refinement will also do that. And so it has the effect of exploring the entire state space of possible sequences of widening, which is huge. But it was nice to know that, you know, there is a principle by which you can explore the predicates, and I think you start essentially with small formulas probably and go to bigger ones. I don't remember the exact details on that, but that was very nice. So we could say something theoretically. In practice, you know, we just stopped the thing after a while. The other thing that was a big hit and spawned, I think, a whole nother research area was this search for ranking functions. So now we're talking about termination of programs, and you and Andre had this. Well, you first had this result that was at MPI. I was taught never to put citations in an abstract. So PR03, does anybody know what that is? Well, you had software model checking with predicate abstraction and termination, you know, in MPI. You were at MPI at that time, and you had this cool idea of transition invariance. But here in this paper, which was the number one cited one, you had this amazing method for proving termination of unnested program loops by synthesizing linear ranking functions. And it was a really cool paper. I definitely recommend people looking at that. And you can basically solve a system of linear inequalities you derive from the program. And if you can get a solution, you can actually synthesize the ranking function. So again, it's a relative, it's a relatively complete method. Again, if there exists a linear ranking function, this method will find it. If it's not linear, good luck to you. Right. So here's a little example with a loop where I think I is strictly, what is I strictly? I is strictly non-increasing, and j is strictly increasing, I believe, in that one. And you get these inequalities, and actually in this loop you can just look. The ranking function is it's just obvious, right? The ranking function is I minus j if I minus j is greater than or equal to 1. But your method would take any program, right, of a particular form and then derive this. So really, really nice. And this started a whole area of work with termination. You and Byron and Andre put it into a tool that was also run on device drivers. A lot of great stuff came from that. Okay, how am I doing on time, by the way? Okay, wonderful. Okay, so now we're ready to move to the postlude. Here we are, Andreas, you and I. You're sitting by the fire, your feet are in a blanket. I'm trying to play the drums, but I never learned how to play the drums. Look at me, it's pathetic. Okay, so what's happened since our days? Well, one of the things that obviously has powered the industry, and as a manager, I was really very lucky to hire great people. I hired Leonardo de Mora, who had already been working on Yikes's and Sal, and he started Z3 with Nikolai Bjorna. And there were many people who we hired into Microsoft Research who then said, okay, SLAM was great, but I can do better. So we had Synergy and Yogi, which was Aditya Nori. We had Solver for reachability modular theories. That was Shah's. Akash Lal and Shivendu Lahiri worked on angelic verification. So one of the things that happened with static driver verifier is there were about 4 or 5 different engines that over 20 years replaced SLAM, which was great to see. I mean, it was sort of like, oh, you know, there goes the baby, but that's progress, right? So really, you know, we were at the start of really something magical, and it was great as a manager to see, you know, all this happening. At the same time, you know, all good things must come to an end. So here's static driver verifier. I think this is maybe the first public announcement. 2024, Jakob Lichtenberg, who we hired in 2003, he told me, Tom, I have some news. Static driver verifier is being deprecated. So it's a 20-year run for a tool. So rest in peace, static driver verifier. But there are lots of good things that are still going on from all those days. We not only have software model checking, we have automated test generation, safety checkers, interactive functional verification. These are slides I used for years and years. Z3 and other automated theorem provers like it are powering automated test generation. These are tools still in use at Microsoft today for binary fuzzing, parameterized unit tests. Daphne, I hear, is getting a lot of use over at Amazon. Rustin Leno started that well over 10 years ago at Microsoft Research. F-star, you might have heard about as well, is also still going gangbusters. So although static driver verifier is being retired, there's a lot of other tools that have come out of the software model checking milieu that are with us and still getting a lot of use. And then of course back to software model checking. The Corral is the latest engine that was in static driver verifier and SimDiff, and those are still, I believe, active projects. At the same time, we've had many other software model checkers, and Dirk and Andreas had this wonderful review. If you haven't seen it, 20 years and beyond software model checking. So there we are, back in 1999. Probably Java Pathfinder. What was the reference there? I don't know what it was. But it predates SLAM. I'm sure there was something before SLAM, yes. And this is the growth of software model checking in terms of citations, right? Search results. And from their paper also, SVComp. So if you know, SAT solvers and SMT solvers all have their competitions, but as software model checking has gotten more prevalent, there have been benchmarks here. And I believe Corral has been used in one of those competitions as some other model, base of some other model checker. So thank you very much for this review. And you know, it's really been amazing to go back and see all the progress. In fact, let's bring it back in the close to device drivers. So the prompt for this was, a robot on a sled being pulled by Samoyeds over a snowy bridge. And the AI came up with that. So even though static driver verifier has been put to bed, we still think about device drivers, automata, and inference. So in closing, what have I been doing for the last 8 years? You can come to the talk. I've been thinking about embedded programming and this thing called the microbit. So it's all about device drivers. So we're teaching kids how to write device drivers, Andreas. We're not using model checking anymore. But just a little bit about what I've been doing. There's something called the BBC microbit. It's been out there since 2015 with 8 million in over 60 countries with a web app called Make Code that's teaching kids how to program these things via a web browser. And then we have a little plug-and-play system so that they can extend this. So think of this as your motherboard. This is your computer, and these are the devices you're going to plug in. And so it's all device drivers, all again. And so there's a shameless plug for my talk at the end of PLDI. Please come to it, JACDAC, service-based prototyping. So I left formal methods for a while, but I've always been thinking about device drivers. Meanwhile, as I was reading your DVLP, I saw this paper, Craig versus Newton. So if anybody knows about abstraction refinement, Craig interpolation was like a big deal. But we had this algorithm that I came up with called for analyzing the trace of a program, and we named it Newton because Newton discovered things. It's stupid, right? But we were young. And we wrote a tech report about this, and I think we submitted it somewhere and it got rejected. But at that time, we were so busy trying to deliver the tool, we were just like, forget about it. So we had this pearl of an algorithm. I think it was interesting, and we didn't even get it published. We were so busy. But you guys formalized it, and then you compared it. So that was awesome. I didn't even know about this until this talk. So, wow. Our comparison of the Newton algorithm variance against Craig interpolation shows that Craig interpolation is clearly outperformed. Oh, this poor person who was just like, let me do something. I was just like, what? And then, of course, you spoiled it at the end. The conclusion one may be tempted to draw from the outcome of the experimental evaluation, maybe that Newton wins over Craig. Okay, blah, 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 blah. But but actually, thank you so much. That was a real gift. I hadn't been working in this area, and I'd always thought, oh yeah, there was that algorithm we never actually published. SLAM had so many ideas in it. We tried to publish it in the beginning with all the ideas packed in, and everybody was like, go away. So we broke it up into pieces, but we never got that piece published. So I have a gift for you. I've been working with Margus Vianis. I think you know who he is. And I think we're onto something big. I mean, you talk to Margus and you get sort of infected by his enthusiasm. We still haven't gotten it published, but we have symbolic automata, omega regularity, modular theory. So actually I'm back. And I recommend looking at this. But in particular, if you want to know more behind the thinking, it's really Margus. The guy's a genius. And he has a little paper about symbolic derivatives and transition regexes. And the way I will say it is like, we love automata, right? But you lose something when you go down to control flow graphs. As we know, if you're out at the program level with formulas, you have algebraic reasoning. When you come down here, complement and all this stuff, it's like determinization, blah, blah, blah. It's interesting to say, what can you do up top before you go down? And so Margus has some really cool ideas. And derivatives are a very old idea, but there's a huge amount of power left on the table there. So Andreas, what's next? Learning specifications. For me, what am I working on? I'm actually doing this now. I was talking with Ahmed about it. Learning specifications of APIs from observable behavior. It's a very old topic. We're looking at automata, abstraction, model checking, inference. You should come visit us. Comparing and contrasting different approaches, and in developing some benchmarks. So I wanted to end with a chorus of thank you. Thank you, Andreas. This is our latest dog, Eowyn, and we actually have another. I know this is going to get rather religious. We have a new baby coming. His name is Moose, and we all very much appreciate all your dedication to software model checking, to automata, to computer science, to theory. And if you don't mind, I will actually let somebody sing to you now. She's a dog who has been away from her owners for 3 weeks, and I just got this 2 days ago. Let's see what's going to happen. Oh no, we can't hear her. Oh, it's horrible. Well, there she is. She's very lonely, and she was singing. You'll have to believe me. Let me see. Oh no, we don't have. It doesn't appear we have. The demo gods are not with me. Let me try one more time. We're going to try one more time. But anyway, that's Eowyn singing for you. And so we thank. Oh no, I can do the singing. Yeah, I can do the singing. I can tell you what I auditioned. We probably have to move on, right? So Andreas, thank you so much. I will let you listen to Eowyn howling for her owners. We've been away for 3 weeks. Yeah.
We do have time for a question.
Oh wow, goodness. Yes, please.
Just a remark. So I gave this talk on the completeness of abstraction refinement in front of Patrick Couzeau. It was a great talk, I thought, and everybody was enthusiastic. And then Patrick Couzeau, I know the difference between software model checking and abstract interpretation. Software model checking does terminate. So that was his comment, to just. And he was bitter about the talk. He said people came to him and said, "Oh, now widening is obsolete," and so on. So
All right. Well, there is Eowyn, and she is happy for you, but sad for her owners. There she is. Oh, so sad. Oh look, yeah, I don't know why the sound's not coming out. I think there must be some setting on the computer. Okay, we'll let it go. Any other questions? There she is, singing for you.
Did Boolean abstraction make it to SLAM at some point?
Oh, you mean, yes. In fact, I remember sitting with Byron. So we had, we had an algorithm that did fix-up. So it actually was by Satyaki Das, I think. I think that's the name. So there was basically, you could figure out in the trace where the Cartesian abstraction was biting you and add constraints. So yeah, we actually had a loop inside a loop. we had this loop where we would check. It was Satyaki Das, and I think Shivendu maybe pointed us to that algorithm. Then Byron and I implemented that. So yes, we did fix up, but we didn't compute precise Boolean abstraction up front. We still did the Cartesian abstraction, but then we did this fix up as needed. Yeah.
So since Thomas is too modest to say this, I mean, Thomas implemented also this refinement that then gets you Boolean abstraction in shape analysis. So this was probably 2010, right? And
Yeah,
what was what was the algorithm?
You mean
The title of the paper?
It was. I'm trying to remember.
Yeah. It's too long ago.
Okay, hold on, I have it.
I'm so sorry. What happened? What's the matter? I gave you a chewy. Is that what's the matter? You didn't like the chewy? You think I was going to abandon you?
She can sing with the object in her mouth.
I see. Oh, okay.
There we go. All right.
Let's thank Tom again.